So we can have the other thing now. We can look at now creating relations in SQL, right? So for creating the relation in SQL, we use the data definition language, or the DDL. So SQL basically consists of two flavors, the DML, data manipulation language, and DDL, or data definition language. So basically, as far as the creating the relation is concerned, we will be dealing with the DDL, or data definition language. And when we talk about the data definition language, there are different functions, right? For example, create table statement is basically a DDL, or data definition language. So we are creating a table. The name of the table is students, and these are the different types of variables and their data types defined over here. So basically, the create table statement creates the students relation. You should observe that the type domain of each field is specified and enforced by the DBMS whenever tuples are added or modified. It means whenever we create a table, these things would be verified, right? So this would be it's important information. So whenever we are adding data or modifying the data in this relation, the name is students, these constraints would definitely be looked and enforced by the DBMS. So as another example, the enroll table holds the information about courses that students take. So we have this create table, name of the table is enrolled. Again, SID is character 20 characters. Course ID is again 20 characters, and grade is of 2 characters. Another point that we can notice that we also have statements for destroying and altering relations. For example, to destroy or delete a relation of students, we can type drop table students. So drop table students destroys the relation students. The schema information and the tuples are deleted. It means the schema and the instance, both of them are deleted when you execute drop table statement. We can also change and alter a relation or a table by using the alter table statement. So we are typing over here alter table students. Students is the name of the table, and what is the alteration that we want? Add column first year of type integer. So when this would be executed, what would happen? The schema of students is altered by adding a new field every tuple in the current instance is extended with a null value in the new field. That is the idea. So basically, when this new field, which is the first year, is added, all the values of this particular field in all the tuples or rows is having a null value in this new field. Then we can have the statement for adding and deleting tuples, and for inserting a single tuple we can use the insert into command, insert into the relation name. And what are the fields that we can insert? SID, name, login, age, GPA. And what are the respective values for these fields? SID 53688, name Smith, login Smith @EE dash, age 18, and GPS 3.2. So basically there's a matching, one-to-one matching between the data name over here and the values that would be inserted. And we can also delete all tuples satisfying some condition. For example, name equals Smith. So what we can do, delete from students S, where S.name equals Smith. So this will delete all the tuples where name is Smith. And there are powerful versions of these commands available, and we looked at them later on. So after that discussion, we come to the most important part regarding the relational model, which is basically the integrity constraints ICs. What is an integrity constraint? Condition that must be true for any instance of the database. For example, domain constraints. Initial integrity constraints are specified when the schema is defined, and integrity constraints are checked when relations are modified. So basically integrity constraints are specified with the schema, and they would be checked whenever relations are modified. For example, if a new row is added, the integrity constraints would be checked, and if the new rows is okay according to the integrity constraints, then only the new row would be inserted, not other way around. So a legal instance of a relation is one that satisfies all specified integrity constraints. So what is basically a legal instance? Legal instance is a relation that satisfies all specified integrity constraints. So DBMS should not allow illegal instances. So any violation of the integrity constraint should not be allowed by the DBMS. If the DBMS checks integrity constraints, stored data is more faithful to the real world meaning and avoids data entry errors too. So what is the meaning of the last point? So when these integrity constraints are looked after, the data entry errors can be avoided, right? So data can be more correct. Now let's look at primary key constraints, right? And what is a primary key constraint? A set of fields is a key for a relation if, number one, no two distinct tuples can have the same values in all key fields, right? So we are referring to in all key fields. It means that key field can be a single field, or key field can be a combination of key fields. Remember our discussion previously when we used course ID, right, along with the SID as primary key, and then when we saw that if a faculty member teaches the same course in different time periods, that information could not be recorded. Or more particularly, we can refer to that particular scenario where an employee used to work in the same department, the same employee used to work in the same department at another point in time. Remember? So if we only had the key fields of the employee's SSN and DID, department ID, then that data could not be entered. Because if the same employee works in the same department for another time period, only the from and to fields would change, and the SSN and the DID would remain the same. So if only SSN and DID were only the key fields, we could not enter the data. So what did we do for that particular scenario? We also had a ternary relationship in which we specified duration using the from and to key fields, and so we had the resultant field consisting of 4 key fields, and that was the combination of the SSN, DID, from and to. So a set of fields is a key for a relation if no two distinct tuples can have the same values in all key fields, right? So key fields would be distinct in all the tuples, in all the rows. Key fields cannot repeat. This is not true for any subset of a key. For example, let's considering the previous example of SID and CID, or in other words, if we take the example of the employee, the department, employees SSN and employees DID, right? SSN might repeat and DID might repeat, but the combination of SSN and DID cannot repeat. And for that matter, if we had the from and to field also as key fields, so the combination of all these 4 key fields would be unique, but any of the key fields could repeat themselves. But if part 2 is false, which means that all the key fields are distinct, then we have the concept of the super key. For example, let's look at the students relation, and when we look at the students relation, we can see that this is the students relation, right? So we can see that SID is unique for all the tuples, and GPA is also unique for all the tuples. So if we have a super key, if we have a key consisting of SID and GPA, then SID and GPA's combination would be a super key, because SID is also unique and GPA is also unique for the instance. Over here we see the extent of the data. You might argue that the GPA might repeat, but in this condition, with this amount of data, the GPA is not repeating. Similarly, SID is also not repeating. So indeed, for this set of relation with this data, the combination of SID and GPA is a super key. So if there is more than one key for a relation, one of the key fields is chosen by the DBA to be the primary key. And again, summarizing this, SID is a key for us, for students, right? What about name? Name cannot be, right? Why name cannot be? Because the name is repeating twice, right? So the set SID, GPA is a super key, like we have discussed before. Now there is also a concept of primary and candidate keys in SQL. Possibly there can be many candidate keys specified using unique. Now when we specify any field using unique, we know that that value should be unique. It should not repeat, right? So candidate keys can be specified using the unique keyword, and from different candidate keys specified using unique keyword, we would select one which would be our primary key. So for example, for a given student and course, there is a single grade, right? This is the usual business rule that holds, that for a given student and course there is a single grade. But we can also have specified wrong integrity constraints, and so we could have a situation in which students can take only one course and receive a single grade for that course. Further, no two students in a course receive the same grade. What does it all mean? Can you relate this to these definitions? Any student? Let's see, let's have an exercise, right? You have this definition of enrolled, and you have this definition of enrolled. I would like all students to insert 2 rows each in each of these relations, right? And let me know. So what do we get the answer? For the first case enrolled, what is the primary key? SID and CID. So this should be unique, right? So student A receives grade B right, and in course CID, right? So let's say if the student A in CID 1 receives a grade B, now student B, let's call it a different, student C in course 2 receives an A grade, right? So this is okay. This first definition is okay because data can be entered, right? Let's see what happens in the second relation. In the second relation, primary key is the SID, right? So A, and the combination of CID and grade should be unique. So if in course 1 the student gets a B, right? So if students, student C also receives a grade 1 in subject P, or so I'm sorry, I said it the other way around. If the student C in course ID 1 obtains a grade B, can this row be entered in this table? The answer is no. Why? Because 1B is repeating, right? And the combination of CID and grade should be unique. So carelessly, if we implement an integrity constraint, it can actually hinder the storage of data into the database. So properly specifying the integrity constraints is vital to a good DBMS system.